Okay, third time's charm. Let's try this. Recording a video for rigid body vibration here. We're going to use rigid body as a pendulum, try to find out its natural frequency. Looking to try to get it into the form like this right here so we could see what the oscillations would be. So in order to do these, we want to write an FBD and an IBD. And the general way to approach this is to, when it comes to this, is to pick a small angle, right? So we're going to have to exaggerate it a little bit in order to make it clear where the moment arms are going to be. Try this right here. So more or less square, something along those lines. Let's see, right there. And we're setting these equal to each other. And so we're going to take the moments about this point. So there's going to be reactions here, and we'll draw them in, but we're going to take the moments about it so we don't have to find them out. And I believe this is O, so that would be the Roy. Here would be rocks. And the center is going to be right there. It's 1/2 of the length of the square, which is they've defined as B as being 1/2 of the thing. So that's the length right there. And so the weight is acting downward. So it's mass times gravity. And it kind of got in the way of my little a. What I want to do is my vertical right here. So here is the small angle that this thing has moved through. It is also, what we usually do is we assume it's in the process of going. So we're going to go ahead and make the acceleration this direction right here. So this is going to be mass times, and this is the tangential acceleration. We might want to also put in mass times the normal acceleration. And we're going to say that it is going I alpha right here. So we write up the sum of the moments about O is equal to the sum of the effective moments. And I say that because I want to include not only this moment of inertia times alpha, but also the inertial acceleration or inertial forces, you can think of them, that are passing through the center of gravity as we go through here. So on the left-hand side, since we've defined, we usually do counterclockwise as positive, we can see that this is generating a clockwise moment, and we're going to multiply it by B, which is this length, times the sine of theta. That'll give us this length right there. And then these forces don't enter into it because we've taken the moment about them. So here we take a look at this mass moment inertia times the angular acceleration. And we call it alpha up here, but I'm going to call it theta double dot. And then we also want to get this, and we happen to know that the tangential acceleration is going to be B times theta double dot. So we have, and this is also going counterclockwise, that inertial force and causing a moment. So it's MB theta double dot, but you got to remember that is just mass times the acceleration. We also need a distance to be able to make it like an effective moment. So we have another B right in there. We want to replace this I. Right, so by the definition of being a square right here, we get 1/12 m, and it's going to be 2b squared and 2b squared right there, because that's the length of one side, is of each side is 2b. And so let's see, that ends up being 2 times 4 b squared, right? Because 2b squared would be 4b squared, and there's 2 of them right there. So what we're left with is 2/3, right? Because that 4 turns that into 1/3, but we multiply by 2. mb squared is the moment of inertia in terms of the variables here. Plugging this back up into the top, I'll move over a little bit here. mgb sine theta is going to be equal to 2/3 mb squared theta double dot plus mb squared theta double dot. Well, you could see that we could combine these together, and we're just going to get 5/3 mb squared theta double dot. We can also, while we're here, let's get rid of that mass. So we can reduce everything down to negative g sine of theta is equal to 5/3 b. Oh yeah, I also got rid of one of the b's right there, right? Got rid of that b and got rid of one of these b's right here. So we want to put this back into the second order differential equation form, where we gather everything together, and let's bring this on the other side so it's into being plus. So we get 3g over 5b sine of theta equals 0. Now that's not an easy or standard second order differential equation to solve, but it could be if we could turn this sine of theta into just straight out theta. Well, it turns out for small angles, sine of theta is approximately equal to theta. And you can really prove that to yourself in one way is to take a look at a very thin triangle. And what this is really saying is that segment length right there, that length of this side approaches the length of an arc that is between there, right? Because we would have this arc length, this delta s, there's a delta theta. Delta s is equal to, here you go, radius times a delta theta. But we would also see that length right here. Let's call this length delta L. That's between there. That delta L would be equal to r times sine of theta right here. If this is theta, that's in there, right? So for very small things, very small, the arc length and the length of a straight line that are right in there, they start to approach each other and get really small. So that's the, you could also plug it into your calculator if you want to, and you could be sure that if you stick it in keep it in radians, that you would have to find the same thing. So now that we have this 3g over 5b theta, we have this ordinary differential equation. We know that the solution of it is going to have be of the form that theta would be equal to theta m times the sine of the square root of 3g 5b t, and then some phase angle right in here. What this is we have the natural frequency is the square root of this term. This little thing on the bottom of my camera thing gets in the way here. If we wanted to get the frequency of this, right, so this is the circular frequency, but we generally want to have this frequency. And we know that the period, sometimes I use tau for that, the natural period is going to be 1 over this frequency right here. So that would be 2 pi square root of 5b over 3g. Now, one last thing to know about rigid bodies, or a rigid body oscillation that we might want to use, is that because a pendulum is a standard thing, right? It's a very common thing. We would measure our rigid body compared to what would the equivalent length that we would need for just a pendulum on a string that would give us the same results. Well, remember that for a pendulum, the natural frequency is the square root of g over L. right? So therefore, you look at this right here, and 5b divided by 3 would be the equivalent of L. So that's why you see up here, what they're showing is this length, this position A right there, is what we might call the center of oscillation, or oscillating center. Let me see if I have the center of oscillation. Right, so if you want to take a look in the textbook, let's see, in section 19.2 is where this is brought up, but we have this definition of the center of oscillation. So if someone would ask you to find the center of oscillation, now you know how to do it. So let's see, how do I get out of this thing? Go Alt-Tab, go to here, and say I'm done.